What's up, guys? This is Mr. Carlson, C-squared mathematics. We are now on our second to last lesson, 9.1 correlation. So this is our second to last lesson in statistics. So it's been a long ride. I'm really glad that you've made it so far. Let's just get right into it. We're not going to go through bell work, unfortunately. We're just going to get right into the lesson. I do have my Desmos pulled up right here, and this, before we get started, I'm just going to share with you. This right here is what we call the 9.1 correlation and scatter plots. It's in your Google Classroom, just underneath your Desmos statistics links there. Go ahead and click on that so you can follow along, and that would be great. Awesome. Let's get started. What is correlation? What is correlation? We're going to ask, how do I calculate a correlation coefficient and a regression line for a set of data points? So we're going to look at the regression line a little bit more tomorrow. So this essential question is really for 2 days. And same thing for this objective. I can calculate a correlation coefficient by fitting a linear regression. So we're going to see how strong these points truly are. So if I am given a set of data, just a random set of data, let's see how strong this set of data actually is. That's what I really want to find, right? So we're going to wrap up statistics with just basic sets of data. If I'm given a random table of data, how strong is this data correlated? We can figure it out, okay? Awesome. So go ahead and click on that video for the crash course if you want to watch that. If you don't want to watch that, that's perfectly fine. But let's go through an overview. Suppose a psychologist wants to know whether a relationship exists between the number of hours a person sleeps each night and that person's reaction time. How would he or she determine if any relationship exists? Let's think about it. How would he or she determine if any relationship exists? Well, of course, you're going to suggest a statistical experiment, right? In this section, you will study how to describe what type of relationship or correlation exists between two quantitative variables. Those variables are something that research psychologist would have to actually gather and study and observe and survey and put together in a set of data so that they can see what the correlation is. You're not going to do something that intense. You're just going to be going through a couple of examples here. However, by using Desmos, that's what they would do in real life. And then we're going to determine whether or not that correlation is significant. What happens if they aren't significant? Now, by just intuitive glance, we can say that the number of hours a person sleeps at night with that person's reaction time, it is heavily intuitive that there is a strong correlation, right? Now, we just know that based on experience, sure, but if I wanted to actually prove it to be the case, I can survey data. I can do some surveys, which research psychologists would do. I can survey the data and then figure it out, right? So correlations and scatter plots, what are they? Okay, a correlation is a relationship between two variables. The data can be represented by the ordered pairs x and y, where x is the independent or explanatory variable. So we call the x the independent or explanatory variable, and y is the dependent or response variable. Okay? Next, scatter plot. A scatter plot, the ordered pairs x and y are graphed as points in a coordinate plane. Of course. Okay, I'm going to show you that just a little bit today, not a lot. Primarily, I'm going to show you tomorrow, okay, with what we call regression lines. But today, I'm just going to primarily show you what they are, like what is a scatter plot and how are they correlated. A scatter plot can be used to determine whether a straight line, correlation exists between two variables. So a constant correlation existing. So get everything you need down for the notes right there. And then let's kind of look through specific examples on correlations and scatter plots. So right here, this is a negative linear correlated scatter plot. As x increases, y tends to decrease. So as x increases, as this is increasing in numbers, my y's tend to decrease here. Okay? Now this one is a positive linear correlation, whereas x increases, y tends to increase. So as y tends to increase, or as X tends to increase, Y tends to increase. Whereas this one, Y tends to decrease here. Okay? Now notice the slopes. Okay, the slopes almost look like a positive slope. Like this would be a positive slope. Now remember, slope is my M value and Y equals MX plus B. So my rise over run, they are all positive slopes here. Okay, primarily. All right? Pretty nifty. Here's no correlation, so it's just all sporadic, just very, very just odd, just kind of blobbed on there. It's no correlation, very easy. And a nonlinear correlation, this is actually a quadratic. This is what we call an x squared correlation, something that we're not really going to get into, in today's lesson, nor in tomorrow's lesson. If you're in honors, then you would kind of get into those sorts of regressions. But in this case, you're not going to get into this sort of regression. Okay? Sweet. So let's move on. In example 1.1, an economist wants to determine whether there is a linear relationship, because we're primarily going to be concerned about linear relationships here, between a country's gross domestic product, GDP, and a carbon dioxide, CO2 emissions. Okay? The data are shown in the table to the right here. Display the data in a scattered plot and then describe the correlation. And so that's what I have done. So I'm going to go over here, as you guys can see. Let me kind of blow this up to projector mode. I think it'll be a lot better. Okay? So here, we'll go to example 1, and I'm going to actually put this data into a table. So as you see right here, all this data is at a table right here, as you see. So 1.7, 1.7, 552.6, 1.2, 462.3, and so forth. They're all in the data. So what we have to do is simply just put this in Desmos, and then voila, we can get a scatter plot. How do you do that? Well, all you have to do is just go here, go here plus, and then all you have to do is type in table, and then it will automatically give you a table here, and that's when you start plugging in your data. Okay. Oftentimes as well, Math Excel will give you like a little blue box. It'll be like right by the table, it'll be like a little blue box that looks like this. You can copy that blue box. You can literally click on it and then just copy it. And then if you go to Desmos, and what you can actually do is just go to a blank one, like give me a second. I'm gonna do a plus expression. So blank one like this, and just hit Control V or just paste. So you can just paste it here. And what would happen is your table that you copied from Math Excel is just going to be implanted right away into Desmos. It's amazing. Okay, it's truly amazing. This is something that we learned way back at the beginning of stats, if you remember, on our Desmos activity, our Learn Statistics Desmos activity. What we did was we actually pasted that. We learned how to take data and paste it into Desmos. You remember how important that was? I told you it was important. So you can do that here, or you can just copy it by hand if you wanted to. It's kind of tedious, and I don't recommend you do that, but you can do that. So I have this table. Now we want to see if there's a correlation. All I have to do is click on this, and then this is my data. And I can actually zoom fit this to be the case. Now, is there a correlation here? There is. There absolutely is. It does look like it's going up, right? So what we can say is that this is a positive linear correlation. Okay, positive linear correlation. All right, and that is my final answer, a positive linear correlation. So I can also say this. So pay very close attention. I'm not going to write this down. Just hear what I'm saying. As the gross domestic products increase, as the X's increase, my CO2 emissions also tend to increase. So when you're going through Math Excel, you're going to be given two things. They're going to ask you if it's a positive linear correlation, negative linear correlation, whatever. And then they're also going to ask you interpret it. Well, I just interpreted it for you, so pay attention and hear me. So this means as my GDP, my gross domestic product increases, my X's as they increase, okay? As my X's increase, my Y's, my CO2 emissions also tend to increase, okay? I'm not going to explain that every single time, but that's all. That's my final answer. I'm done, guys. Isn't that simple? It's so simple. Remember, if you want to do a table, all you have to do is go to Desmos, and you just have to do plus and then table, and then it would automatically register a table for you, and you can just copy down the data here for my X's and my Y's. And then they will automatically plot their scatter plot for you, okay? I just have them preloaded because, like I said, it's just easier during my lesson. Awesome. So let's erase this. Let's move on to our next example and go a little bit faster here. So a director of alumni affairs at a small college wants to determine whether there's a linear correlation or linear relationship between the number of years alumni have been out of school and their annual contributions in thousands of dollars. The data are shown at the table below. Display the data in a scatter plot and then determine the correlation. So these are my X's right here. Yes, these are my X's and these are my Y's. So all I have to do is go over here and I already have it available for us. So this is 1, 10, 5, 15. That's my X's. And then here are my Y's. What's the correlation? Let's find out. So I plug on this and I can always click on this button here. You see where my cursor is? It's called Zoom Fit. So right here, it's kind of hard to see. Like, what is that? Well, if I click on this, it would zoom fit it. And so it kind of zoom in. Your camera would kind of zoom in for Desmos and see what the correlation is. So what's the correlation? It looks like this is a negative linear correlation. That's my final answer. So what does that mean? As the number of years out of school increase, my X, as that increases, my annual contributions in thousands of dollars tends to decrease, which makes sense. The more you're out of school, the more you're not going to give to the school because you're probably dead or you have other financial obligations like retiring and so forth, right? So you have that kind of mentality. Make sense? Awesome. So I hope that's awesome for you. Let's erase and let's go on to example 2. So 2, I'm going to click on that, go over here, and let's go to example 2. So a student conducts a study to determine whether there is a linear relationship between the number of hours a student exercises each week and then the student's GPA. So these are my X's for hours of exercise. My GPA is my Y's. Let's see if they're correlated. I have them all listed right here. Remember, just make a table and I can put them right here. And I click on it. Let's do zoom fit. Is that a correlation? No. Okay, that is not a correlation at all. So what I would say is no correlation. Okay, no correlation. That's my final answer. There's no correlation because it just looks like a big blob. There's no correlation between the number of hours a student exercises each week and the student's related GPA. There's no correlation there. See how simple that is? It's awesome. It's very, very simple indeed. Really hardly any mathematics involved, just using the calculator. Example 2.2. Let's scroll down and let's do this. This is my other example. So a researcher conducts a study to determine whether there's a linear relationship between the person's height and the pulse rate. So do you think that there will be a linear correlation? This is my X, this is my Y. Okay? You can kind of tell just by looking at the table, the X and Y's, if there will be a linear correlation. And if we click on it, we could do zoom fit. Doesn't look like it. Okay? Doesn't look like it at all. There is no correlation there. It just looks like a blob. So I'm going to go over here and just again say no correlation. Guys, I'm telling you, it's that simple. Okay? That simple. Easy stuff. Very simple stuff. So let's erase that and let's continue. So example 2. This will be example 2.2. Okay? Example 2.2. example 3. This should be example 3. So let me change that real quick because it should definitely be example 3, not 2. Awesome. So example 3, Old Faithful, located in Yellowstone National Park. World's most famous geyser. The duration in minutes of several of Old Faithful's eruptions and the times in minutes until the next eruption are shown in the table at the right. So this is a long table. And as you see on my Desmos program, on my Desmos, you see all of these values. So I painstakingly transfer them over. Okay, painstakingly transfer them over. Now again, remember on Math Excel, more than likely, you'll see a little blue box that'll be right by the table. What you do is you copy that, and then paste it into Desmos. All you have to do if you're on Desmos, just get a blank little space here, and then just hit Control V, Control on your keyboard, and then V. That will paste it in there, and then it will automatically give you your table. Okay, pretty nifty stuff. Pretty nifty stuff. So make sure you know that. Okay. So we want to determine if it's correlated. Let's see if it's correlated. Let's click it. And again, it doesn't show up at all. That's fine. Scroll down and then go ahead and click the Zoom Fit button down here where my cursor is. The Zoom Fit button. That's going to allow you to see it kind of a little bit more clearly. Maybe. Let's do Zoom. There we go. Okay. Awesome. So that's my Zoom Fit. Awesome. So I clicked on it, and that's what I get. Now, clearly, this is a positive linear correlation. So that's what I'm going to write. Positive linear correlation. Okay? That's my final answer. Why? Because as x's increase, as my duration increase, my time also increases. As the durations of the eruptions increase, the times until the next eruption tends to increase. Okay, as you can clearly see, this is going up that way, up. Okay, sweet. Make sure you are using Desmos to display the data in the scatter plot. It's way easier. So let's go to my next example. So the correlation coefficient, what we've done so far is calculate a lot of different things. We've calculated really just the scatter plot, and we've seen the basic positive or negative or no linear correlation based on the scatter plot and data. So now what are we going to do? We're going to do what we call the correlation coefficient, an actual number that tells me how strong a scatter plot is. Let's just say this scatter plot of Old Faithful. Let's just say this scatter plot right here is in fact strong. Okay, it is in fact a positive linear correlation, and we were correct. It is a positive linear correlation, right? A positive linear correlation. However, watch. How strong is that linear correlation? We can calculate that using the following formula. So I'm going to show you what the formula is, but using a following formula. Although a formula for the sample correlation coefficient is given, it is more convenient to use Desmos. Okay, so let me say that again. Although a formula is sufficient for the sample correlation coefficient, it is more convenient to use Desmos. As you can see here, I will be using Desmos to calculate this number. So now here's where the actual math comes in. Okay, here's where the actual math comes in, where we're going to be using Desmos to find a certain number. But it is so simple. It is so easy. Literally, like, I think a caveman can do it because it's just that simple. All right? Now, interpreting the correlation coefficient using the scatter plot can, in fact, be subjective. Sure, because what I can really do, guys, is just interpreting the correlation of a scattered plot. I can just say, hey, that's pretty strong, or that's positive. Now, I can tell whether or not it's positive or not, but it is still subjective. If I want a more precise and objective way to calculate what I call the correlation, I can use the formula. So let's go there. All right, here's the definition. The correlation coefficient is a measure of strength and direction. So it's a measure of strength and direction, so whether it's positive or negative, but also how strong this relationship is. So if I want to know how strong two variables are connected together, like Old Faithful's eruption and time, or height and weight, or GPA and exercising, if I want to know how strong they are connected together, I can use what I call the correlation coefficient. The symbol R represents the sample correlation coefficient. Now, why is it the sample? The reason why it's the sample is because, again, I'm not looking at all of the data. I'm only looking at a select few pieces of data, and then I'm performing math on that. If I was looking at the whole of the data, I would be looking at the whole population. But I'm not looking at the whole population, so I only want the sample here. What is this formula? Now, we're not going to be doing this by hand. However, I feel like it's necessary to thank our lucky stars to look at this formula and say, oh, shoot, I don't need to do that. So I'm going to give you the formula, but you do not need to calculate this by hand. You do not need to calculate this by hand. Now, Math Excel will probably tell you to calculate it by hand, but I'm telling you to not calculate it by hand. Do you understand? I just like to give the formula so that students can be appreciative of the Desmos that we have. So this is the big, long, nasty formula. N sigma, which is the adding of x times y minus the sigma, or the addition, or the sum of all x's times the sum of all y's. This is all over, okay, this is all over, in parentheses, my radical, I know it gets really intense, n times the sum of my x's squared minus the sum of x's squared. Okay? And then I'm going to multiply that by the exact same thing, but with my y's. Okay? With my y's. Now watch. My n times the sum of my y's squared minus my sum of y's squared. This is the correlation coefficients formula, and it is awful. It is gross. Is it not? This is really gross. So we're not going to be doing this. We're going to be using Desmos. Okay? So with that said, I just like to give you the formula just in case. Now, n is the number of pairs of data. Now, the population coefficient is represented by rho. That's basically, it looks like a little ph or a p there. It's represented by rho. We never really calculate the population correlation coefficient. That's going to be for advanced mathematics and advanced stats. We don't need to calculate that. We primarily calculate the sample correlation coefficient. So let's get into the properties of what this correlation coefficient looks like. And then after we get into the properties, then we're going to start doing some math on it and then finish out with some analysis or inferences. So what are some of the properties? Well, the range of the correlation coefficient is literally from -1 to 1 inclusive. That means I can only include numbers. When I calculate this out, my correlation coefficient is only between -1 to 1, which means it cannot be 2. It cannot be 5. It cannot be 1.2. 1.00009. No, it is not that. I swear to you, if you literally put in 5 on a correlation coefficient answer, when it's simple, when all you need to do is go to Desmos and type it in, I will lose my freaking mind. Okay, it is that simple. It's so simple. Like I said, literally a caveman can do it. You guys can do it. I promise you. You just need to pay attention. The correlation coefficient is only between -1 to 1. You will not get any other number other than -1 to 1. Now remember, what does that actually look like? On a number line, what that looks like is this. This is -1. This is 1 with 0 in the middle. You can only have numbers in between these two. Okay? So I cannot have 2, 5, 6, 7 because that's on the other side of this 1. I can only have numbers less than 1 and numbers greater than -1. That's it. I can have 0. I can have negative 5.7. I can have positive 0.57. Okay? Instead of negative 0.57. But that's what it would look like. I need to stress that. Now, when X and Y have a strong, what's considered a strong positive linear correlation, R is close to 1. So it's close to 1. Positive 1. When they are said to have a strong negative linear correlation, it's close to -1. When X and Y have a perfect positive or negative correlation, that means it's literally a straight line. It is a straight line. That means R is equal to 1 or -1 respectively. When there is no linear correlation, okay? When there is no linear correlation, R is close to 0. Or roughly, if there is literally no linear correlation, it is 0. Okay, but it's gonna be very difficult for you to actually get 0. It may be like 0.00157. That's not necessarily 0, but it is close to 0, something like that. And then last note, if R is close to 0, this does not mean that there is no relationship between X and Y. It just means that there's no linear relationship. Okay, so when I calculate this, when we calculate the correlation coefficient, all that means is that there is no linear relationship. There could be a relationship, and you probably will get a number, but there's no linear relationship. All right? That's all it means. So, just to kind of recap, what is the correlation coefficient? What does it look like? Well, if I have something like this is a perfect line. I mean, that is a perfect straight up line. Because that's a perfect line, my R will be said to be equals 1. This is a perfect positive correlation, positive linear correlation. Here, this is a strong positive linear correlation because I can write a line in between here, right? I can do a line in between here. It's not perfect, but I know it roughly goes up, right? It approximately goes up. Yes? Yes. So we can say that this is a strong positive correlation. Now notice my R is close to 1, but it's less than 1. It's not greater than 1. It's just close to 1. This is what we call a weak positive correlation. Now it does kind of go up, okay, roughly, but it's still kind of scattered everywhere, and so we say that this is a weak positive correlation with R equals 0.45. Let's go through another slide to kind of see what some strong negative or weak negative correlations look like, and then we'll get to some examples. So this is a perfect negative correlation. I mean, just a perfect line that goes negative. Okay, so this is R equals -1 because it's perfect. This does go down, and it is very, very strong. It's not an exact line, but it has the same shape or so as a line. So this is what we call a strong negative correlation. Okay, a strong negative correlation, right? And notice how the R is negative 0.92. It's close to -1, so it's a really, really strong negative correlation, but it's still negative. And this is virtually no correlation at all. I mean, it's basically just almost 0. There's no correlation here. I can't even draw a line either way. It could be negative, it could be positive, I don't know. So this is what we call a no correlation, when it's very, very close to 0 here. All right, so I just showed you some examples of correlations. Now let's go through some actual examples using our previous questions to calculate these correlation coefficients. Are you ready? So calculate the correlation coefficient for the gross domestic products from example 1.1. So I'm going to use example 1.1. All right. So what does that mean? I'm going to look at this table. This was example 1.1, the gross domestic products right here, right? Now watch what I do here. If I go right here and I zoom fit this, okay? Notice what I'm doing here. Watch. Watch. I'm labeling this X1 and Y1. You see that? Pay very close attention to what I'm about to do here. This is X1 and Y1. Do you see that? X1, Y1. This is the one I'm interested in. This is the gross domestic products. This was example 1.1, yes? This was example 1.2 down here where my cursor is. This is example 1.1. I want 1.1. This is the correlation. We said it was a strong positive correlation. Okay? How strong exactly, though? Let's find out. Actually, what we just said was it was a linear, a positive linear correlation. That's all we said. It was a positive linear correlation. Now, is it a strong positive linear correlation? That's what we want to try to find. How am I trying to find that? I'm going to show you right now. But watch. This is X1. This is Y1. Think about that. I'm going to close this. Now go to example 4. Look at this. X1, Y1. All I must do on Desmos is literally type CORR, 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 and then parentheses, and then I put down the X1 or Y1 or the X label or the Y label that I had in my original table. So if my table says X1, Y1, okay, that means I'm going to write my correlation CORR X1, Y1. If you don't want to type that, you don't have to. Watch. You can go down here to your actual functions menu, and then you can click on functions. You can click on stats, and then you can click on CORR right there. That's all you need to do. CORR right there. Okay? But of course, I don't want that. So, does that make sense? Now I can actually see this to be the case. Look at this to be the case. Look. What is my correlation coefficient? It is literally that number. So my correlation coefficient, my R, equals 0.912. This is my correlation coefficient. Now we have to interpret it. What does this mean? Since this is close to 1, we're going to say that this is a strong positive linear correlation. Strong positive linear correlation. Okay? Because it's close to 1, this 0.912, because it's close to 1, it's what we consider not just a positive linear correlation. I already knew it was positive linear correlation. Okay, we already did this example. We already plotted the scatter plot in example 1.1. Now what we're looking at is whether or not it's strong. Well, this is a very strong positive linear correlation. Perfect. That's what it's entailing. Awesome. I hope that makes sense. Now let's go to example 2. So example 2. Okay. If I go to example 2, or sorry, example 1.2. So let's go to example 1.2. So I'm going to scroll down. This was example 1.2, the number of years out of school and the annual contribution. Okay. This is what it was. If I click on this and then zoom fit, this is what I see. So it does decrease. Let's scroll down and now notice. This was X sub 2. See? X sub 2. I labeled it X sub 2. And this is Y sub 2. Which means you are going to type in CORR to find your correlation coefficient, and then X sub 2, comma, Y sub 2. What's your correlation? It's that. So my R equals negative 0.908. This is actually rather strong, but what we would say it is a strong negative linear correlation. Strong negative linear correlation. Okay? We already knew it was negative linear correlation. We already knew that. But now what we're trying to find is whether or not it's strong. And so it is strong because this is close to -1. And I know it's negative because it says a negative. Okay? Guys, this is literally it. This is all you must do. I honestly cannot comprehend how anyone could mess this up because I've laid it out so perfectly for you. That's very, very simple. When you go to Math Excel, when you actually do your Math Excel homework, you're going to see examples literally exactly like this. And all you have to do is go to Desmos. You don't need to go to this exact Desmos link. You could just go to a blank Desmos graph if you want, a blank Desmos graph, and then just start going in, plussing your tables everywhere, and then copying down the data and just type in CORR with whatever X value or Y value your table is given, whether that's X sub 1, X sub 2, doesn't matter. And then you get your correlation coefficient. That's literally the whole homework. That's it. Okay? So let's erase this and let's continue on in our examples. Example 5. So let me erase this, get done with that. So calculate the correlation coefficient from the Old Faithful data in example 3. So this was example 3. This was our Old Faithful data. I'm going to go ahead and blow that up. Notice how this is X sub 5 and Y sub 5. Okay. That's my Old Faithful data right there, as you can see. Yes. So this is X sub 5. Notice that. Y sub 5. I want to find the correlation coefficient of that data. And so I already have it down here for us. Let's go to example 5. Way down here at the bottom, do you see that? That's the correlation coefficient for that data. So what is that? That means my correlation, my R value equals 0.979. This is extremely, extremely strong. This is a very, very, very strong linear correlation. Strong positive linear correlation. I already knew it was a positive linear correlation. Now I'm trying to see whether or not it's strong, and my correlation coefficient tells me objectively that it is strong. Okay, because it is very, very, very close to 1. See this? Extremely close to 1 right here. Okay? Sweet. So that is how you do the correlation coefficient. Let's go through our last thing, something that we actually don't need Desmos for, unfortunately. We don't need Desmos for. We're done with the Desmos link. By all means, if you want to use this Desmos link, do so. Okay, it's up to you to use it to kind of follow along with the notes, but also during the homework. Now, let's get into what we call the relationship between causation and correlation. Now, the fact that two variables are strongly correlated, just like the ones that we did right now, does not in and itself imply a cause-effect relationship between the variables. So that does not mean that something is causing the other thing. So even if they're strongly related, let's just say that it is strongly the case that me not getting enough hours of sleep and my reaction time are strongly correlated. Just because that's true does not mean that because I don't have a quick reaction time, the reason for that being I don't have a quick reaction time is because I don't get enough sleep. It could be some other reason. Maybe I thrive on not getting enough sleep, and then I do have a quick reaction time. I mean, it just depends. It depends on a variety of factors that are unbeknownst to us. So here are some conditions that you should consider. Is there a direct cause and effect relationship between the variables? You should consider this before actually insinuating whether or not that the correlated variable does indeed provide a good causation for the other response variable. You're going to ask yourself, is there a reverse cause and effect relationship between the variables, between the explanatory and the response variable? You're going to ask, is it possible that the relationship between the variable can be caused by a third variable? Maybe it is. Who knows? Or perhaps a combination of several other variables. And last, is it possible that the relationship between two other variables may be a coincidence? Because it could, in fact, be a coincidence. We don't know. So these are good guidelines to think of. Make sure you get them down. Pause the video if you need to. Okay, so let's go through our last example. A person breaks out in a rash after eating shrimp at a certain restaurant. This happens every time that the person eats shrimp at the restaurant. What is the cause of the sickness of this relationship? Can we be certain to know why or why not? Well, I'm just going to verbally speak it. I'm not going to write it. Well, honestly, guys, it may seem like this relationship between eating shrimp and going to the restaurant and you eating the shrimp is the cause of your sickness. However, just because it seems that way does not mean, just because there's a correlation, does not mean that the shrimp has caused your sickness. So, in other words, we cannot be certain that the cause of the sickness, the problem, the cause of the sickness is what is giving you the allergic reaction. So, in other words, we cannot be certain that the shrimp gives you the allergic reaction. Even though it's strongly correlated, it does not mean that the shrimp is the sole cause for the allergic reaction. It could be something else, such as a seasoning to the shrimp. It could be maybe the air in the atmosphere. Okay, maybe it's maybe some other food that you're allergic to there that you're eating with the shrimp, or maybe that you're sniffing with the shrimp. Some allergies just affect you just by purely being around them, such as cat allergies. If you're allergic to cats, all you need to do is just be around cats and then you start being allergic, right? So you could be allergic to something else other than shrimp, but though you keep eating shrimp because you really like shrimp. It could just be something else in the restaurant. You don't know, right? So you cannot be said to have certain knowledge that the shrimp is what causes your sickness. It is correlated, but that does not mean that it is caused. So that is really interesting. I love talking about that kind of stuff. It's very interesting to think about. It's a little bit philosophical even. Okay? But what did we learn? What did we learn? We learned how to introduce linear correlation and then independent and dependent variables. We learned how to find a correlation coefficient and how to test a population correlation coefficient using a table. We kind of did that, but not really. Okay, and then perform a hypothesis test for a population correlation coefficient. We did not do that at all. But we also distinguished between correlation and causation. Okay? So guys, make sure you are working on your homework. Be sure to do your notes. Until next time, guys, this is C Squared Mathematics. Be sure to like and subscribe.